Hello, everyone. If you find soft robotics appealing, then you will be interested in the results that me, Cosimo, Kosta, and Adriano prepared. In this paper, we deal with the adaptive control of soft robots based on an enhanced 3D augmented rigid robot matching. So there are many ways one can control a soft robot. One way is based on model-free machine learning techniques that consider a soft robot as a black box. A different approach relies on model-based techniques that take into account the infinite dimensionality of a soft robot. On the other side of the spectrum, we have model-based approaches that leverage on approximated but finite dimensional models. Our paper can be placed in this third group with the difference that the soft robot is modeled in such a way that classical control theory can be directly applied, though under certain assumptions. The first assumption is that a soft robot can be approximated as a series of constant curvature arcs, or in other words, it is a piecewise constant curvature. This kind of assumption allows an effective kinematic control. A step further has been made by connecting kinematics and dynamics of a planar soft robot with the augmented rigid robot. In this way, one can achieve a dynamic feedback control. Moreover, this method has been extended to a soft robot that is moving in a 3D space. However, this model has a small limitation that in the straightforward configuration it suffers from singularity and discontinuity. So this has been overcome in the recent work where improved parameterization has been used instead of theta I and phi I angles. In our paper, we capitalize on the advantages of both augmented formalization and improved parameterization. So let me explain it better. Regarding improved parameterization, each segment can be described with delta x, delta y, and delta L variables, where delta x and delta y are calculated by using the length of 4 arcs of each segment, and delta L presents the elongation of each soft robot segment. Then it is a well-known result that each segment of a soft robot is kinematically and dynamically matching a 10-segment rigid robot. The configuration variables of a rigid robot are xi, and they have no linear dependency on variables of improved parameterization. So we can achieve even further result that stands for the whole soft robot if we conclude that since soft robot is made of series of constant arcs, then we have a mapping that is decentralized and global and stands therefore for the whole soft robot. Let us now move on to derive a dynamic model for a soft robot. And in that process, we start from rigid robot dynamics. That is well known. In this case, configuration variables have a size of 10n, where n is the number of arcs and 10 is the number of rigid robot segments per each arc of a soft robot. Then, if we leverage on the mapping presented in the previous slide, we can reach an intermediate step in deriving soft robot dynamics. In order to complete a soft robot dynamic model, we as well need to include the block diagonal elastic friction and actuation terms. And herein you can see the full model. There are two amazing properties that stand for this model. First one is that the inertia matrix is positive definite, and the second one is that the Coriolis matrix has a skew symmetric property. And these two fantastic propositions have literally opened the door to the application of a classical theory control approach. So far, usually parameter-dependent control has been developed and used for soft robots, like a computator controller or Cartesian impedance regulator. However, you can imagine that a soft robot has incredibly variable physical characteristics, and even if you make two soft robots of the same design, they will never have the same parameters. And this fact has motivated us to apply adaptive control. In order to be able to apply this technique, we first have to satisfy two hypotheses as exposed in the work by Slotin and Lee. The first hypothesis regards full actuation of our system. And since we use augmented formalization, then it is possible for us to model a soft robot as a fully actuated rigid robot according to propositions 1 and 2. The second hypothesis that has to be satisfied is that the dynamics has to be linear with respect to parameters. Or in other words, we need to have the ability to write the dynamics of robots as a product of a regressor matrix Y and a constant parameter vector P. So let's take a closer look at how to satisfy this hypothesis. And again, let us start from the rigid robot dynamics, which, as you probably already know, can be expressed already as a product of regressor matrix and a constant parameter vector. Moreover, each addend of rigid robot dynamics can be expressed as a corresponding product of a regressor matrix and a parameter vector. Then we lean again on the mapping present in the previous slides, and we notice one very handy thing that Jacobian of mapping can as well be expressed as a product of regressor and the parameters vector. And this leads us to the following calculations of soft robot dynamics. So by substituting this mapping into rigid robot dynamics, we obtain this result that each addend of a soft robot dynamics can as well be written as a product of a regressor matrix and a parameters vector. So we can conclude in the end that soft robot dynamics can be written as a product of one regressor matrix and a parameters vector. And satisfying these two hypotheses leads us now to the main result of this paper, and that is the theorem on the adaptive control, which says that given a soft-bodied robot described by this equation, we can derive the dynamic control law that is consisting of a parameter update law and a calculation of the input torque. And that ensures asymptotic tracking of any desired trajectory vector signal QD. Here on the right side, you can see the block scheme of our controller. And now let me tell you how to prove this theorem. So in proving this theorem, we lean on the conclusions derived by Santina and Lee in their work. So the first amazing thing about using this approach is that you can avoid using acceleration measurements if instead you introduce the reference speed QR dot. And that is exactly what we do in our dynamic model. There is a difference with respect to the approach presented in this literature, and that is the fact that we have an actuator matrix multiplying the input torque, which is not considered here. Therefore, we need to define a new input, tau star, that is equal to the product of actuator matrix and input torque, and where actuator matrix is precisely known and invertible matrix. Later, one can reconstruct the input torque tau by using the pseudo-inverse of an actuator matrix. And the rest of the proof follows from Santina and Lee. Okay, let us now proceed to the results. We've really wanted to test the boundaries of the adaptive control when applied on a soft robot. So we started with applying adaptive control on a planar soft manipulator. And we assume that we have an initial tracking error equal to 1 radian. Then we assume that we have a complete lack of knowledge of parameters of our system. Therefore, we set their initial value to 0. Then we include the measurement noise and the disturbance at around 25 seconds. So here in the top row, you can see the result when soft robot is controlled with gains that have mild values. And as you can observe, tracking error has some larger value in the beginning, but over the time it diminishes. And all the configuration variables successfully track the desired values. Here in the middle plot, you see that parameters remain bounded and that the commanded torques successfully deal with the disturbance that acts in the 25th second. Here on the rightmost picture, you can see the evolution of a robot shape, where with the green color, we present the shape of a robot in the initial position. Blue color presents the position in the final position of the robot. And with the grayish color, you can see the intermediate positions and shapes of a robot. If now we use control gains that have higher values, so we impose a stronger control action, then you can notice that the tracking error has a faster convergence to 0. And you can see from this rightmost plot that the robot has a less clumsy behavior. Okay, let me now move on to the application of adaptive control to a soft inverted pendulum. We have been very excited with this result because this result showed the robustness of the adaptive control to the model of a soft robot. So in this case, pendulum has an affine curvature and it does not have any more piecewise constant curvature approximation satisfied. So moreover, we also in this case assume that we have some initial tracking error, that we have a complete lack of knowledge, and as well we added some measurement noise and disturbance. So you can see this in the top row that starting from some initial position, our pendulum manages to come to the upward straight position. In the top row, you see the result when stiffness is small. It is just 1 Newton-meter over radian, and that's why the pendulum swings a lot while returning to the upward position. In the lower set of figures, the stiffness is equal to 4, and that's why the pendulum does not swing so much. Moreover, you can see that it can successfully deal even with the disturbance and the measurement noise. Finally, we apply our result on a soft manipulator that is moving in a 3D space. And this has been a computationally most challenging case for us. So again, there is some initial tracking error that the controller successfully deals with. There is a complete zero knowledge of parameters and disturbance of 5 Newton acting at around 50 seconds, which controller manages to diminish over the time. So thank you very much for your attention. If you feel like further discussing about these results, then feel free to contact me on my email address. See you.